I'm Anil Kumar. Before getting into details of solving differential equations, it is important to understand what they represent geometrically. So here we'll talk about two terms. One is slope fields, the other one is direction field. They will be used like in a very similar way. The only difference is direction fields, whenever you draw, will have arrowheads. The slope fields will be small line segments. Now, slope fields are graphical approach to look at all the solutions of a differential equation. And slope fields consist of short line segments representing slope or steepness at the points x and y. So if you are given a differential equation dy dx equals to fxy, then you can geometrically interpret this as dy dx is the slope, right? So at any point xy, the slope at that point is given by the function f of xy. So that is what it is. We'll take these three examples and sketch slope fields for them and then interpret their meanings. The examples are dy dx equals to minus y plus 2, dy dx equals to minus sin x, and dy dx equals to minus xy. So here the slope is just a function of y. In this case it is function of x, and here it is function of both x and y. Then we'll talk about in details slope fields and how to interpret a lot of information, a particular solution also when initial conditions are given with the example dy dx equals to y times 1 minus 1 over 4 y squared. So let's take them one by one. The whole idea is only to understand slope fields and not really solve differential equations. Here is the first example to draw slope fields. Let us consider the differential equation dy dx equals to minus y plus 2. As you can see, the slope dy dx is dependent only on y and is independent of x, correct? So here, horizontally, if you move along, slope is going to be exactly same, correct? So whenever you have to draw slope fields, it's always a good idea to take the coordinate points. Now since dy dx, or rather I should say slope, is just minus y plus 2 independent of x, there is no point taking x values. So we'll only consider the y values and we'll calculate the slope. Always to begin with, we have to look for easy values. So first is y equals to 2. So if I take a value of y as 2, for example, then minus 2 plus 2 is 0. Now 0 means horizontal is going to be the slope, right? That is 0 slope. So at y equals to 2, all these points we can mark horizontal short segments. These short segments are actually the slope fields for y equals to 2. So any differential equation solution curve will be tangent to these points. That's the whole idea, correct? Now, if I take a value more than 2, let us say if I take a value which is 3, then what happens? If I take a value 3, minus 3 plus 1 is negative 1. So negative 1 means a slope will be going downwards like this. So all along this line, we can draw short line segments with negative 1 slope, right? Downward. Do you see that? So we get slope at all the points at where the y value is 3. So if I take y value of 1 now, for 1, minus 1 plus 2 is plus 1. So we get plus 1 means a slope like this. So that means these short lines diagonal, right? So this is your slope 1. Now whenever we are drawing the slope fields, we don't put any arrows. But if we do direction fields, we put arrows. So that is another very subtle difference between the two. Now if y value is 0, then what? If y value is 0, the slope is 2. 2 is steeper than 1. So I'll make a line which is kind of like this, right? So all along the x-axis, the slope is going to be kind of like this, steeper than what we had drawn earlier, right? So that's how it is. So all along the x-axis, these are parallel short segments with slope of 2. Now if I take minus 1, then what? Minus 1 will make this positive and we get plus 3. So it is positive and 3, steeper than earlier 2, right? So it is kind of like this. So at minus 1, it is even steeper than this. So let's go like this now. So what you observe here is that if the values are at 2, we have horizontal slope, all the y values less than 2, positive slopes. And as we go down, they're becoming steeper and steeper. Do you understand? They are steeper and steeper. So if I take minus 2, then minus 2 makes it plus 2, plus 2 plus 4, and this is very steep. So we'll end here actually. So it's kind of very steep, right? So that is what it is. Almost like a vertical line for me at present, right? So that becomes the slope. Now I think from this pattern, you can see a lot about the solution of your differential equation dy dx equals to minus y plus 2. So we have done part 1, which is to sketch slope fields. Now let's answer the next question, which is find equilibrium equation. What is that? Equilibrium equation. So when we say equilibrium equation, it really means that the equation which is kind of horizontal, where the slope is 0. So from here, the equation is this. That is equilibrium equation for the value y equals to 2. You would also get equilibrium equation by directly solving this equation. So what you could do here is you can equate minus y plus 2 equals to 0, and that gives you y equals to 2 as your equilibrium equation, right? So I hope that part is also absolutely clear. Now let's look into the next question, which is when is the solution a decreasing or increasing function? So as you can see here, if you have values more than 2, the slopes are negative. So it is decreasing for, so let me write out clearly here. Okay, so decreasing for y greater than 2, it is decreasing. And when is it increasing? If the y value is less than 2, all slopes are positive, correct? All slopes are positive. So all this, where y is less than 2, we have increasing function. But if it is y is greater than 2, in that case, we have decreasing function. So I hope that is clear. Decreasing because the slope is negative. So if I go to 4, it'll be more decreasing kind of, correct? So that is how it is going to be. The last question here is, what happens as x approaches infinity? Now if x approaches infinity, you see all these curves, they actually approach towards 2, right? So when x approaches infinity, it approaches a value 2, the equilibrium position. Do you see that part? Correct? Now you would always, to draw a particular solution, what you could do is select a point. So if you select, let us say, a point here, which is at minus 1, 0. So if I select a point minus 1, 0, I could sketch a particular curve. The whole idea is when you sketch a curve, then this segment should be tangent to your curve. So that is how you have to sketch it. So basically it will be kind of like this. So that curve indicates solution, a particular solution whose initial value is given to us. any other curve you could select with some other value. For example, a curve above 2 will kind of look like this, decreasing. Do you see that? So I hope that gives you a fairly good picture of what this differential equation represents. That's the whole idea. Now let's move on and take another example. This time we have a function where the slope changes with x. It is independent of y, correct? So let's discuss this now. Now we will consider the equation dy dx equals to minus sine x. We need to sketch the slope fields as we did earlier, and we need to sketch a graph of a particular solution where the initial condition is 0, 3. That means it will go through this point 0, 3, right? That's what it has to be. We have to do. So first step is we have to look at slopes at every point. So we'll consider a few points which are important to us, and from there we can draw the conclusion. Let me first change the horizontal scale. When we talk about the trigonometric functions, we'll like to write the values in radians. That would be actually a better option, right? So beginning from the left side to the right side, we could take values, let's say 0 in between, right? So we could go pi by 2, pi, 3 pi by 2, 2 pi, correct? So those could be values on the right side, and on the left side we'll go minus pi by 2, minus pi, minus 3 pi by 2, and minus 2 pi. Is it okay? So those are the points which we are going to take. So I'll accordingly change. So we are having how many points? This is 0, 1, 2, 3, 4 on the right. So I'll just change them, right? So this we'll call pi by 2. Then this we'll call as pi. And then we have 3 pi by 2. And then we write this as 2 pi. Is it okay? Forget about those. So we have this as minus pi by 2, minus pi, minus 3 pi by 2, and minus 2 pi. Okay. So those are the points which we are going to consider on the x-axis. Now sine x. For x equals to 0, what? So whenever we look at the sine curve, let me just sketch a sine curve on the side. And that's easy to pick up all the values, correct? Sine curve is kind of like this. Remember, we have minus sine, so I have to reflect it. But basically, that is the sine curve, right? 0 to 2 pi. Okay. So let's take each and every point, starting with 0. So sine of 0 is 0. So sine of 0 is 0. That means we're talking about slope which is horizontal. So wherever it is 0, it is going to be horizontal. Since y values are not changing the slope, so as we go higher up, it is going to remain horizontal, or as we go down below, it is going to remain horizontal, right? Does that make sense? Okay. So that's one. Now let's take another point, which is pi by 2. So at pi by 2, the y value is 1. Minus 1, since we are working with minus sine x. So here it is going to be minus 1. That means downwards like this. So at pi by 2, it is a downward slope like this. So all along x equals to pi by 2, the vertical will have that kind of slope dropping down. Correct? Now let's take the next value, which is pi. Now for pi, sine is 0. So pi sine is 0, it again means horizontal. So we again have horizontal at pi. So all these values will be horizontal. Then 3 pi by 2. Now when we talk about 3 pi by 2, we are looking at a value which is minus 1. Right? 3 pi by 2 is minus 1. But minus of minus 1 gives us plus 1. That means upwards. So at 3 pi by 2, it will be short segments will be kind of like this. Correct? And at 2 pi, it is again 0. 0 means horizontal, right? So we'll just draw horizontal line segments for 2 pi. Correct? So let's start from the other side. Minus 2 pi is also 0, that means horizontal. Minus 2 pi is right there. So we get these horizontal lines all along the line, vertical line. X equals to minus 2 pi. Correct? As far as minus 3 pi by 2 is concerned, well, this graph actually repeats like this, right? So symmetrical. Now, minus 3 pi by 2 means this is like, come here. So this is 2 pi, correct? And minus 3 pi by 2 is positive 1. So that means minus positive 1, but negative means negative here, right? So negative 1 means it will be dropping down like this. So we have a slope at minus 3 pi by 2, which will be like this. Then at pi minus pi, again it will be 0. So at minus pi it is 0, a horizontal line. And at minus pi by 2 it is negative 1, which will give us negative and negative becomes positive 1. So that will be positive 1, and that means like this. So positive slope of 1. A diagonal short segment gives you the slope field at minus pi by 2. So that is how we get our field, as you can see here, right? That is how it is. So we have sketched the slope fields. Part B is sketch graph of a particular solution where the initial condition is 0, 3. Now, here we have 0, 3 as our initial condition. Now, if I have to sketch a graph, it is horizontal here. On the left side it's coming down. On the right side also it is coming down. And then it has to turn from here. So those horizontal are the turning points. Correct? So how do we sketch it? So let's do that. So what we will do here is that we'll sketch, this becomes a tangent to our curve, and it has to turn like this. So it is kind of like this. Do you see that? So that is how it is going to be. So it will turn from all the horizontal points, and these short segments are the tangents. So you have to be very careful. In all these short segments will become the tangents as you go along. Now, since you start with a maximum, it is a cosine function, correct? So that is the solution. You know, derivative of a cosine function is minus sine x. So it makes sense. So that is how we can look at the solution from the slope fields. So I hope this point is well taken care. Now let's take the next example, and then we'll do a question in more details. So as we are moving along, we are adding some complexity. We began with function which was independent of x, then we took the trigonometric function which was independent of y, and now we have a function which depends on both x and y. So we will consider the differential equation dy dx equals to minus x over y. Now here we need to sketch the fields for the differential equation, describe all locations in the xy plane for which the slope is undefined, and then remove one part. Sketch graphs of solution that satisfies the initial condition 0, 3. So we'll sketch a graph going through 0, 3, right? So that is what we have to do. Now here there are very interesting things. Before we get into sketching, let's try to analyze what we have. So we are saying that the derivative, which is a slope, is dependent on the function itself, and at any point x and y, the slope is given by ratio of x and y with a negative value. Correct? That's what we say here. Now, I'll just plot x and y values. Let me do it horizontally this time. So what we will do here is that we will write x values, y values, and the slope, which is their ratio with a negative sign. Is it okay? That's what we'll do. So what do you observe? If I put y as 0, then what happens? Then for any value of x, it does not exist. Do you see that part? That is very important. If y is 0, that means along the x-axis, it does not exist. It means it is not defined, right? So I'll make small holes here. All along this x-axis, I'm going to make some holes here. It only means that it is not defined at this point, correct? So that's very important thing. Now, what happens for any value of x, right? For any value of x, that is the scenario. Now, if I take the value of x as 0, let's now take x as 0, then of course we'll consider all y's but not 0, right? All y's but not 0. So we can write here that y is not equal to 0. Is it okay? In that case, the slope is going to be 0. That means horizontal. Is that okay? So whenever x is 0, it is horizontal. That means all along the y-axis, it is horizontal. Let me draw here also small segments. At 0.5, I'm drawing. Okay. Fine. So we get the 0 points. It is good to analyze and then substitute the points. Otherwise, this job becomes very tedious. Now, if I take x equals to y, let us say x equals to y. So now I'm considering the point where x is equal to y. That means points like 1, 1, 2, 2, 3, 3. Then what happens? If x is equals to y, right, in that case, we get minus 1 here because they are same, right? So slope is negative 1. That means dropping down. So that means along this diagonal, it is dropping down. So that becomes the slope along this diagonal. Do you see that? So we'll not touch the x-axis. There it is not defined. But all of the places we could draw this. Correct? Now what happens if x equals to minus y? If x equals to minus y, then we have plus 1 slope, right? So x equals to minus y means we are in quadrant 3 or in 4, right? So they are like negative of one another. So here it is going to be positive 1. So we could draw these as positive 1 slope. Correct? So all these are positive 1. Correct? Now, we can take some other values for x and then draw. For example, now if I take x as minus 1, then for different values of y, what do we get? So if I take x as minus 1, let us say, then this becomes positive reciprocal of y. Correct? So for minus 1 and 1 we have already drawn. But if I take minus 1 and 2, then it becomes half. That means lesser slope. Do you see that? It is lesser slope, kind of like this. And if it is 1 over 3, then it becomes even lesser. Even lesser. Do you get my point? But if it is less than 1, it means if I take half as the value, it becomes 2. So it is more slope. So that is what happens when y value is positive. But if y value is negative, then in that case, it becomes negative. For half, it becomes negative 2, steeper, right? For 1, we have already drawn negative. And if it is 2, then it becomes half, less steep, but negative. And if it's 3, it is even lesser steeper, right? So more towards horizontal. Do you see that? So that is how the slope will be if we look into this side. Now similarly, if I look at x equals to plus 1, then we are getting negative of y values. That is to say, if I take x as plus 1, that is along this line, and y as 2, then we have negative 2 slope. So it is dropping down like this. Negative 2 is just steep, right? I mean half. So less steep. So at minus 1 it is kind of like this. And with 3 it is even lesser steep because it is 1/3. Correct? So it is negative up to here. But as soon as the y value becomes negative, it makes that positive. So it becomes positive slope, and denominator increases, slope decreases, and becomes more and more horizontal. Do you get the idea? Correct? Now let's take a value of x which is minus 2. So we're just moving away now. So at minus 2, that becomes minus 2. Minus minus becomes positive. And now we get 2 over 1. So the slope here is 2 over 1. So twice this. Twice this. So it is steeper than this, 2 over 1. So it is twice what we had there. Do you see that? It is twice that we have there. So we could just make slightly more steeper than this point. Do you get my idea, right? So it is slightly more steeper than this. That's what we're trying to say. Correct? If the y value is negative, then negative, it makes it this one also negative. So here all the slopes are going to be negative. Perfect. All slopes are dropping down. And minus 2 over minus 1 is going to be is just 1, right? So at this point it is going to be minus 2 and minus 1 is going to be minus 2. So it will be steeper than this, minus 2. And as we go further down, y value increases, so it becomes more horizontal. You get an idea. So what you see here is kind of a circle. Do you see the pattern here? Kind of a circle. So that is what we observe. Now let's take few more points and then we can draw our pattern. So you can already see the pattern here, which is kind of circular, right? So let's move on and take some more points. So if I take x as plus 2 now, we have already taken 1. If I take plus 2, we have a negative value for y positive. So if y is 1, the slope is 2, negative 2, right? So it is kind of negative 2. As the y increases, the slope decreases. So it becomes kind of flatter. Do you see that? So that is how it is. On the right side, when we go down, slope is 2 divided by 1 minus minus becomes plus. So it is positive. So it is positive here, but as we go down, it becomes lesser and lesser steep. Correct? Similarly, if I take the value of x as, let us say, now 3 minus, right? So minus and minus becomes positive. As the value of y is 1, it is minus 3. That means coming down. Minus and minus is positive, so positive 3 for y equals to 1. So steep, positive 3. As y value decreases, it becomes steeper, and if y value increases, it becomes less and less steep. Correct? Now on this side, since y is negative, slope becomes, for negative 3, positive becomes negative. So we have negative slope here, and as we go down, it becomes lesser and lesser steep, right? So here it is more steep, and then it becomes lesser and lesser steep. So what you see here is kind of a circular pattern. So that is how you can actually fill this up and see very clearly what we are going to get, right? So slope fields, again I want to emphasize, gives you a geometrical look of the solution. So you can appreciate how the solution will look like. Now let's get to the part B now. We have done part A, that is sketching the slope fields. Describe all locations in the xy plane for which the slope is undefined. So it is undefined for x-axis where y is equals to 0, right? We just filled that up with holes here. C. Sketch the graph of the solution that satisfies initial condition 0, 3. Now if I have to draw a graph here, then it should go like tangential to all the points which we have drawn, correct? So we have some fields here. You could have packed this up also. So starting from here on the left side, we can see that the graph goes like this, but we have to stop here. Since that on x-axis, it is undefined. Do you see that part? So that is very important to understand. So similarly on the right side also, it is going to be kind of like this, but as soon as you approach this, it becomes steeper, but you have to stop here. You should not be crossing it. Some students can do a mistake by continuing this and making kind of an ellipse or a circle, whatever. But then, if you do that, it is not a function. It will fail the vertical line test. So I hope it is very important to understand that for different values, different initial values, will have different solutions. These are called particular solutions based on initial values. In general, you may see that it represents kind of a circle, right? So we'll actually take this up in more details later and see what it really represents. But I hope with that you get a fairly good idea of how to sketch slope fields and how to interpret the solution of a differential equation, correct? So let's now, we are almost at the end, and here is the final question for you. With all the information you have, I'd like you to pause the video now, copy the question, sketch, and then see my suggestions. Now let us consider the differential equation dy dx equals to y times 1 minus 1 over 4 y squared. We need to sketch slope fields for the differential equation, describe all locations in the xy plane for which the slope of f y equals to f of x is positive. C is find all equilibrium solutions, and D is sketch graphs of solutions that satisfies given initial condition y0 equals to 1. So these are different conditions, right? y0 equals to 1, y0 equals to 3, y0 equals to minus 1, y0 equals to minus 3. That means we are looking for 4 graphs, right? 4 initial solutions, right? So now, what we have learned here is also how to quickly sketch slope fields. These are short dashes which represent slope at any point on the Cartesian plane. We are given differential equation dy dx equals to y times all this. Now let's find where do we get equilibrium solutions, right? So when we say equilibrium solutions, we want to say slope is 0. Now clearly from here, slope is 0 for y equals to 2, right? So one is at y equals to, y equals to 2 will give me 1 minus 1. If I write 2 here, y squared is 4. 4 divided by 4 is 1. So 1 minus 1 is 0. And 1 is y equals to 0. So these are 2 solutions which are equilibrium solutions. Now at these points, we'll have 0 slope. As you can see, the given differential equation solution is independent of x. So that means, like our first example, all along the y equals to this value will have the same slope, right? So we can draw horizontal dashes along y equals to 2 and y equals to 0. So let's do that first part. And that is also the equilibrium solution for the given equation, right? So these are horizontals drawn as a part of our slope fields. Okay. Now, we also want to know when is this slope field positive. So when I say positive, then it means what? Why? There are 2 factors, correct? So it is going to be positive when both are positive or both are negative, correct? So there could be 2 conditions. So we're trying to answer this. So there could be 2 conditions, that is when we multiply positive with positive, or we do negative times negative. That means this is positive, or this is negative, this is negative. Correct? What I mean to say, these two factors. So when y is positive, that means when we are looking at the upper half, when is the inside function positive? That is to say, if I write y equals to 2, then it is 0, right? 1 minus, if y value is less than 2, then this is positive. So in this period, it is positive, correct? So the function is positive when y is between, when y is greater than 0 and is less than 2, correct? It is positive. Similarly, on the negative side, when both are negative, when is this negative? Now y squared, that term will be negative if it is more than minus 2. So if it is more than minus 2, then it is negative. Does make sense to you? Right? So minus 2, I meant absolute value because y squared, right? And it is between minus 2 and 0. That even for y equals to minus 2, we get a 0. Is it okay? So I missed that part earlier. Here also it should have been zeros. Correct? Since it is y squared, so we get zeros here also. I should have, sorry. When y is less than minus 2. When it is on this side, then this is negative. Let's put minus 3 here. If I put minus 3 here, in that case this is negative, and minus 3 will make that as negative, so both becomes negative, right? So it is negative here. I mean, negative makes it positive. Positive here and positive here. Correct? So in these two portions, it is going to be positive. In rest of the portions, it is going to be negative. That's one part. Now, let's sketch the slope fields taking different values of y, since we know that it is independent of x, correct? It is independent of x. So we'll take different values of y and then we'll write down the slope fields. Calculation is to be done based on this, correct? So if I take a value of y as 1, so we'll write the y values here and we'll write the derivative values or the slope underneath. So if I take y as 1, in that case it will be 1 minus 1 over 4. That means 4 minus 1, 3 over 4. So the slope is 3/4, right? So slightly less than 1. So wherever y value is 1, the slope is 3/4 and it is positive as expected. So y value is 1 along this line. So 3/4 is less than 1. So we'll draw these lines here as 3/4 slope. Correct? If I take minus 1, y value at minus 1, then what happens? So this is again minus of 1 plus 1 doesn't make this 3/4, but that becomes negative 3/4, right? So this becomes negative 3/4. Do you see that? Negative 3/4. So instead of rising up at minus 1, it will be going downwards. Correct? So it is kind of like this. Slightly less than 1, but downwards. So that is what it is. So you see a kind of symmetry here, right? Okay. Now let's take the slope when y is 3. So if y is 3, in that case, positive 3, this is positive. But here, 9 over 4 will make this as minus 5 over 4. Right? So it is minus 5 over 4. So slope is negative and slope is more than 1. Right? So it is coming down negative and it's more than 1. So let's say it's kind of like this. Since it is independent of x, all along y equals to 3, we can draw these short segments indicating the slope fields. Now let's look into minus 3. For minus 3, it will only become plus 5 by 4, since that becomes negative, right? So negative negative makes it positive. So for this, now we are expecting positive as we thought of. So we have positive greater than 1. Correct? So we have more or less filled in the slopes. Now we could take values 0.5 values also in between to fill up these gaps, right? And then get a better graph. Correct? Now the idea is that as the y value is becoming between greater than 2, we are having negative fields, correct? So if I have 2.5, in that case the slope will be slightly lesser than this. So we could do it like this, lesser than this, and we can just mark it here. Right? So that is how the slope will be. And similarly, here if it is the y value is less than 1, it is going to be more, because that is the -1 value. You can calculate all these values and figure it out, correct? Now, so that is how we kind of get our field. Now the question here is, sketch graphs of solution that satisfies given initial condition y0, 1. Now it means what? The x value of 0, y value of 1. That means you are here. So this point is on your solution. How will the solution look like? That's what it means. So if you have to draw a slope field from here, then you know it is going to be tangent to this. It is rising as you go up, and then like this. That is how it is. So the slope will be kind of like this. Do you see that? So for this, that is going to be the particular solution when the initial condition y0 equals to 1 is given to us. Got it? Now let's draw another curve when y is 0 and y0 is 3. That means that x equals to 0, y value is 3. So when we're talking about this point now, so at this point we know the slope is negative, the graph is coming downwards, right? So when we draw it, it is going to be, these short segments going to be tangent, so it has to be kind of like this. So that becomes the graph of the function going through 0 and 3, correct? Now let's take another ink and draw the next one, which is for 0 and -1. So at 0 and -1, we are looking for this type of a function, right? Now here, you can see we are approaching this point. The field here, which I should have drawn, will be kind of like this. You can calculate these values, right? So it'll be kind of like this. So what will happen here is that when you go through the point, which is 0, -1, 0, -1 is right there. In that case, the graph is going to be like this. So it will be like this. So you have to fill up these values to really get to see how it should be looking like. Is it okay? So you should do that part on your own. The last graph here is when y value is 0 and -3. That means here all these functions are positive. It is a rising curve and it rises to equilibrium position of -2. So it's kind of like this. So that is how you could get particular solutions when initial condition is given to you. So in this video, what we learn is that slope fields give us a look and feel of differential equations. They are easy to draw since the derivative is given by the coordinate function itself. So once you plug in the values of coordinate, you know the slope at that point. Make short segments at that point. Once you make all these short segments, you can actually visualize the solution of a differential field. All the solutions of the differential field. To get any particular solution, you need initial values. Once you know the initial values, then you can draw that particular graph, a particular solution represented by the differential equation. So I hope that gives you a fairly good practice of how to interpret solutions of differential equations using slope fields. And now we'll get into details of solving differential equation. Feel free to write your suggestions and comments, and if you like and subscribe, that'll be great. Thanks for watching and all the best.